Previously, I went through the unification process involving the law of universal gravitation, using the same physical principle to show that motion near the surface of the earth and motion in the heavens are the same thing. As impressive as those unification problems are, however, Newton still has to submit a specific numerical proof of his theory of gravity. And he does so in Principia in 1687. It involves the orbit of the moon about the earth. I've presented it to us here as a problem. Go ahead and copy down the problem into your notes as I read it to you. It is perhaps, by the way, the most important physics problem in all of history. Okay, the problem itself I've broken up into two parts. Okay, this is Newton's proof, published in Principia in 1687. Assume that the moon orbits the earth in uniform circular motion. This is done so for simplicity. If you do take into account the elliptical orbit of the moon about the earth, you end up with the exact same result anyway. So we're going to simplify such that it's an algebraic problem. Okay, show that Newtonian gravitation predicts that the moon falls 1/20th of an inch per second. So part A of the problem is the theoretical prediction. And then in part B of the problem, we're going to use the moon's orbital data involving numbers that we have known since the time of Ptolemy to determine exactly how far the moon falls in 1 second. If the theoretical prediction matches up with what actually happens, then Newton's theory of gravity is correct. Now, Newton did not know what capital G was equal to. That wasn't measured until after his death. So how does he get around this problem of not knowing capital G to ultimately submit this proof? Here's what he does. Okay, so part A of the problem is the theoretical prediction. Let's first of all examine what happens if you take an object, such as an apple, for example, and you drop it like so from rest near the surface of the earth. Let's calculate how far the apple is going to fall in 1 second. Okay, now let's say that right here is the earth like so. Remember that mathematically we treat the entire mass of the earth as a point here at the geometric center, and then right here is our apple in free fall near the surface of the earth. As long as we are near the surface of the earth, for all practical purposes, the distance between these 2 points is just equal to the radius of the earth. And now we just have one force being exerted upon the apple, and that's the force of gravity associated with the earth's mass. And so then therefore we write F equals ma in the following way. First of all, we have the force of gravity, capital G times the mass of the earth times the mass of the apple, and then divided by the distance between the 2 points squared. This then equals mass times acceleration, where the acceleration is small g, acceleration due to gravity. Incidentally, by the way, the problem is presented in imperial or English units. So let's just be careful of small g. Small g is equal to 32 feet per second squared. Okay, now let's just go ahead and cancel out the mass of the apple itself like so, and then small g is equal to this value here. All right, now we already know from basic kinematics what the formula is for an object that is dropped from rest to calculate the distance that it falls in 1 second. If we very simply drop the object from rest at the origin, the distance that it falls is discovered through the following expression. 1/2 gt squared. This is a portion, of course, of the kinematics equation for an object in free fall that we examined in an earlier unit. We are just ignoring negative signs here for simplicity. Once again, think of the object as being dropped from rest and being dropped from the origin. So the distance that it then therefore falls, call it small d, is just 1/2 gt squared. So this is 1/2 times 32 times a time here of 1 second squared. Let's note that this is 1 second. So then therefore the distance d, very simply, is equal to 16 feet. Okay, and now we go from the surface of the earth to the location of the moon. How can you think of the moon as falling? We'll do so in the following way. Okay, so now here's the moon's orbit about the earth, like so. Right here is the earth with a mass m sub e. Let's say that right here is the moon with a mass m moon. And on this diagram, let's think of the moon as moving clockwise on the diagram. So then therefore at this moment in time, at the moment that I've drawn the diagram, the moon is moving in this direction like so. Think of the moon as a projectile, like for example in the monkey hunter demonstration. Recall what I said about that demonstration about how you can think of a projectile. You can think of a projectile as falling below a line. below a line that it would have traveled if there was no acceleration. So then therefore at this moment, the moon is moving in this direction. Think of the moon as falling below that line, much like, for example, in the monkey hunter demonstration. What we want to calculate is, according to the theory, how far below that line is the moon going to fall in 1 second. Okay, now we have one force exerted here on the moon, and that's the force of gravity. The distance, by the way, between the moon and the earth, I'm going to label here as small r. So now let's just write F equals ma. So we have the force of gravity, capital G times the mass of the earth times the mass of the moon, and then divided by the distance squared. This then equals the mass of the moon multiplied by its acceleration. I'm going to refer to the acceleration as g moon. So this is the acceleration due to gravity at the moon's location due to the Earth's gravity. This is not describing what happens if you take an object and just drop it at the surface of the moon. It's not that. It's acceleration due to gravity at the moon's location due to the Earth's gravity. Let's go ahead and cancel out the mass of the moon, like so. Okay, now g moon is equal to the following value, like so. And then what do we do at this point? Well, it has to do with small r. Small r is the distance from the moon to the earth. We've known that distance since the time of Ptolemy. It was first measured by Ptolemy 2,000 years ago. Earlier in class, I described to you that measurement. I also described Ptolemy's result. Ptolemy's result is very accurate. This is why that number is so important. And I mentioned its importance briefly back in that lecture on Ptolemy. The distance from the Earth to the moon is 60 Earth radii. So now we go to Ptolemy. Small r is 60 times the radius of the Earth. So let's go ahead and plug that into here in the denominator of the expression. So capital G times the mass of the Earth divided by 60 times the Earth's radius squared. 60 squared is 3,600. So we end up with 1/3600th of this quantity. Like so. So take a look at that carefully. I squared the denominator of the expression. And now, this quantity here, you'll notice, is small g at the surface of the Earth. So then therefore, acceleration due to gravity from the Earth's gravity at the moon's location, it's 1/3600th its value here at the surface of the Earth. Very simply, just think of it like this. Because gravity obeys an inverse square law, we go from the surface of the Earth to a distance that is 60 Earth radii further away. So then, therefore, acceleration due to gravity should be 1 over that distance squared of the original value. 1 over 60 squared is 1/3600th. So basically what we're examining here is really nothing more than the inverse square law. Now, what about the distance below this horizontal line that this projectile falls? Let's call that distance d moon. Okay, now from basic kinematics, the distance that the moon falls below this horizontal line, just think of it that way, this is equal to 1/2 g moon times t squared, where once again small t is 1 second. Okay, now acceleration due to gravity at the moon's location, once again this is due to the Earth's gravity, is 1/3600th its value here at the surface of the Earth. So d moon is going to be 1/3600th of 1/2 gt squared. Notice what I did there. And then this distance here from the top board is 16 feet. So according to the theory, the distance that the moon falls in 1 second below this horizontal line should be 1/3600th of 16 feet. Let me go ahead and determine what that number is. So 16 and then divided by 3,600. And then I'm going to multiply this by 12 inches per foot. So multiply by 12 inches per foot, and it comes out to be 0.05 inches. 0.05 inches is 1/20th of an inch. Now, 1/20th of an inch is an extremely tiny distance. That's like the distance between my thumb and my index finger right here. That distance there is about 1/20th of an inch. According to the theory, the moon falls that distance below this horizontal line in 1 second. And now let's calculate what actually happens using the moon's orbital data. That's part B of the problem. So this right here is the theoretical prediction. Let's now see what actually happens. That's part B. So part B now is what actually happens. Well, we only need two numbers to determine what actually happens. Let me begin by drawing out, however, the following diagram. All right, so right here is the moon's orbit about the Earth. Right here is the Earth like so. Let's say that the moon is right here. And now in a time small t of 1 second, the moon moving along the following line would travel the following distance on this diagram. The moon would move like so in 1 second if it wasn't falling as a projectile. Okay, we're going to give this distance here a name. I'm going to refer to it as S. Okay, and then we have the distance from the Earth to the moon. The distance from the Earth to the moon here I'm going to refer to as small r. Small r is known. It's been known since the time of Ptolemy. It's 60 Earth radii. However, we do need that number in terms of inches. So how many inches is 60 Earth radii? Well, it's rather large, as you might imagine. I do actually have it written down in my notes. It's the following number. It's 151,338 52,800 inches. That distance there is 60 Earth radii. Once again, we've known this distance since the time of Ptolemy. Okay, now on this diagram, let's go ahead and complete your right triangle like so by drawing in a hypotenuse. And then the distance from here to here is once again small r, and then right here is the unknown. This is the distance that the moon falls below this line in 1 second. This is what we're trying to find. Let's call it D moon. Okay, now we can determine what D moon is by just using a little bit of Pythagorean theorem. Before I use Pythagorean theorem, however, we do need to know this distance here. This is the linear distance that the moon moves in 1 second. So this distance S here is equal to the speed of the moon multiplied by the time of 1 second. The speed of the moon, however, is 2 pi r divided by its period multiplied then by small t. Here's the other number that we need. The other number that we need is not the synodic period of the moon, it's the moon's sidereal period. This is why this number is so important, and I briefly mentioned its importance earlier in the previous lectures. Now, capital D, one sidereal period, it's roughly 27 1/3 days or so, but I do have the number written out in terms of seconds. So in terms of seconds, it's 2,360,590 seconds. This right here is the sidereal period of the moon, its true orbital period. Okay, now using these numbers, let's go ahead and plug everything into here and then figure out what S is equal to. Okay, so I've got, let's see, 2 times pi, and then times that gigantic number for small r, so times 151,338 52,800, and then divided by the period, 2,360,590, and then multiplied by small t of 1 second. And in terms of inches, that distance is 40,282 inches. This is the linear distance that the moon moves in 1 second. Okay, now I'm just going to go ahead and complete the calculation here by doing some Pythagorean theorem. All right, so here's how the Pythagorean theorem works in this problem. We have here r² plus s² equals then the hypotenuse squared, which is the sum of small r and d moon, like so. Now let me go ahead and FOIL out here the right-hand side of the expression. So when I FOIL out the right-hand side of the expression, I end up with this. Like so. So take a look at that carefully. I just FOILed out the right-hand side. And now let's go ahead and start to simplify. Okay, when I simplify here, notice immediately that the r squareds cancel. Like so. And then take a look at this. Take a look at d moon squared. Remember what d moon is predicted to be. It's only predicted to be 1/20th of an inch. So compare this number squared to, say, this number here, which has the big number r, or this number here, which has the big number s. Notice that d moon squared is negligible compared to those other values. So let's just go ahead and discount it, like so. And now, because that is negligible, let's just go ahead and solve for the remaining d moon. So d moon is going to be equal to s squared, and then divided by 2 times r. Let's see what this number is equal to. So now, once again, this is what actually happens. All that I'm doing here is using the moon's orbital data, numbers that we have known since the time of Ptolemy. So I still have s in my calculator. Let me square that. And then divide it by 2r. So 2 times 151,338,52800. And after all of that, we end up with the following. 0.05 inches. 0.05 inches is 1/20th of an inch. The fact that this number, what actually happens, matches this number here, the theoretical prediction. This then tells us what about Newton's theory of gravity? It tells us that Newton's theory of gravity is correct. Newton has solved the problem. He has unified motion in the heavens and motion at the surface of the earth as the same thing, and he has provided for us here a numerical proof of his theory in Principia. However, let me conclude this extremely important lecture in the following way. If you think about it, however, Newton's theory of gravity looks and smells like magic, because here's basically what Newton is saying. He's saying, for example, that you have two objects such as the sun and the earth separated by 150 million kilometers of empty space. There is nothing there. Yet somehow magically, the sun is able to reach across that distance and instantaneously exert a gravitational force on the earth, causing the earth ultimately to remain in its orbit as it orbits the sun. To Newton and his contemporaries, that looks and smells like magic. However, Newton's defense of his own theory very simply was this. Regardless of what gravity may be at a more fundamental level, it makes mathematical predictions, such as this number here, predictions that can be tested. And that's exactly what we did here on the top board with what actually happens as the moon orbits the earth. There is a very famous quote attributed to Newton that has to do with this topic. He basically said, "I feign no hypothesis." What he meant is that regardless of what gravity may be at a more fundamental level, it works this way mathematically. It makes testable predictions and it passes those tests every single time. That was good enough for Newton in terms of gravity. And that was actually good enough for our description of gravity for about 2.5 centuries. So you can now think of Newton in the following way. Newton is basically the guy who invented physics and then therefore modern science as we know it today. And his theory of gravity was basically good enough as a picture for about 250 years. But 250 years after Newton, somebody else came along and reinvented physics. That was Albert Einstein. We'll get to him at the end of the year.